All right, so I want to start with a famous story, um, usually attributed to the Greek philosopher Zeno. And you might have heard of this before, so if you have, just bear with it. But if you haven't, think about this. The first person that told me this was my fifth grade teacher, and I couldn't figure it out then. And I don't think she had it figured out. But it had been figured out. It has been figured out. And you could even pause the video in a minute. Maybe you could figure it out yourself. Let's see. I have to look at this right here. Right now, my hand is not. This is really not good the way this is lined up right now. But right now, my hand is not touching this whiteboard. And if it's going to touch this whiteboard, it'll have to cross this halfway point. So say here's the halfway point here. Now it's halfway towards the board. My hand's halfway towards the board. Is it touching the board yet? Nope. Is there a new halfway point? Yep. Will I have to cross the new halfway point before my hand touches the board? Yep. So I'm at the new halfway point. Am I touching the board yet? Nope. Is there a new halfway point? Yes. I'm at the new halfway point. Am I touching the board yet? No. Is there a new halfway point? Yes. Will I have to cross the new halfway point to get to the board? Yes. Okay, I'm at that halfway point. Am I touching the board yet? No. Is there a new halfway point? Yes. Will I have to cross the new halfway point before I touch the board? Yes. I'm at that halfway point. Am I touching the board yet? No. Therefore, you'll never touch the board. At the same time, there, I touched the board. And that was considered a paradox. If you want to know more about it, just look up Zeno's paradox. So you can get all kinds of information. It turns out there is a solution for this. And it may seem strangely simple. So I would like you to consider the following. Oh, you know what I should have said? Of course you can't touch the board. There will be an infinite number of halfway points. And how can you cross an infinite number of halfway points? There will always be another halfway point, and you get to that, and another halfway point. Now, in terms of modern physics, there may actually not be another halfway point, but I want to dispense with that for a minute. So, depending on what results of our quantum mechanical way of looking at the world, the universe, the structure of the universe, of space, time in particular, there may actually not be a new halfway point. And that would be interesting to go down that road and talk about that, but this isn't the place or the time. So consider the following. Oh, so the point is you can't do an infinite number of things in a finite amount of time. Or can you? So consider this square, a 1 by 1 square. What's the area of this square? 1 times 1, the area is 1. I would normally say stop me if I say anything wrong. Or if this is complex or complicated. See, hopefully you're thinking, what could be easier? It's a 1 by 1 square. The area is 1. Continue on. I would like to chop the square in half. So this is, here, I'll chop it in half. And here, I'll go ahead and label that. That line segment right there is 1/2. This is still 1. What's the area of this rectangle? Well, 1/2, because it's 1/2 times 1. Chop this rectangle in half. So it's a 1/2 by 1/2 rectangle. It's a square, but rectangle. What's the area of that square? Well, it's 1/2 times 1/2, which is 1/4. Chop this in half. So this would be 1/4 and 1/2, and 1/4 times 1/2 is 1/8. And I think you start to pick up on the pattern here. And I could chop this in various, I don't have to chop it this way, but it's kind of a neat way to chop it. The area here would be 1/16, and chop it like this. And the area would be 1/32. Chop, 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 chop. There'll be no end to your ability to keep slicing this up in half. What does this picture prove? This picture proves the following. It proves that 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and you add an infinite number of terms. Because if I don't add all infinite number of terms, all areas for those rectangles, it won't equal 1. It would get arbitrarily close, but it wouldn't equal. But if I add all of them, an infinity of terms, this equals 1. Now let's go back to the paradox of the fact that you can't cross the board. Hey, again, if you go online and you look up Zeno's paradox, you'll see there's all kinds of formulations. The hare and the tortoise and a variety of different things, but they all amount to the same thing. But notice, suppose it took half a second to reach the first midpoint, a quarter of a second to reach the next one, an eighth, a 16th. In 1 second, you would have crossed all the midpoints. You would have done an infinite number of things in a finite amount of time. And hopefully you'll let this sort of sit with you and think about it. Because this is opening up a whole, I was going to say new can of worms, but it's opening up a whole new field or whole new avenue in mathematics. And we're only going to begin it here. And this is in chapter 12. Chapter 12 is called Sequences and Series. And this would be an example of what's called a series here. And these numbers, 1/2, 1/4, 1/8, 1/16, if you think about them one after the other, not necessarily added up, but if you just think about them as a collection of terms, then that's called a sequence, and they're ordered. One of the things I think people find very confusing about this chapter is this seems to come out of nowhere, or why would anyone want to do such a thing? So let me just tell you up front. There are reasons. And if there were no other reasons, I could at least tell you one, and that is every calculation that you've ever done using a calculator has done something like this. It turns out that this is what's going on behind the scenes every time you use your calculator. Are there other uses for sequences and series? Yes. Thousands, millions, billions, I don't know, an infinite number. But yes, there are reasons. And yes, this is something that is worthwhile to learn. And if nothing else, when you finish chapter 12, I hope that you have an insight into something about the way we write numbers, in particular with decimals, that very likely you didn't before. So this is a pretty short video. I want to finish with one final little thought. And I would just like to give the definition. And I'm going to be pretty loose with these definitions. These all can be made much more precise, but we leave that for later courses. But a sequence is, well, here, I already wrote down a sequence. Let me write it down again. 1/2, 1/4, 1/8, comma, dot, 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 dot. Now, this doesn't have to go out to infinity. Maybe I want this to terminate at 1/2 to the 10th. And oftentimes we use these funky brackets to indicate that what we have here is a set of objects. In this case, it's a set of numbers. And we do tend to think of these as being ordered. This is the first term, second term, third term. This will be referred to as the nth term, as in the letter N. That's probably because we think of these as, well, first, second, third, fourth, fifth, or 1, 2, 3, 4, 5. These are the natural numbers. So N sort of corresponds nicely with that. 2 to the 10th is 1024. So this is a sequence. Unfortunately, the term sequence and series, they're easy to confuse because they both begin with an S. But a sequence is a list of terms, and the sequence may be, I should have started off with an easier one. Here's an easier one. Ready? 1, 2, 3. And that is the set of natural numbers. I mean, technically, we don't include 0 in the set of natural numbers. It's for technical reasons in the field of number theory. When you're proving things, a lot of times you don't want to consider 0. For example, blah, 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 blah. You can do the following as long as it's not 0, for example, division. But at any rate, this is an infinite set, and it's a sequence, and this one happens to have a particular name. It's a set of natural numbers. Here would be another one. I could have started, I could have started with this. I'll start with this: 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Now, I could terminate it there. I could just end. I could have this be the entire sequence, or we could say dot 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 dot, which is to say it keeps on going, and that is an infinite set. So a sequence is just a set of objects, and they're ordered. So there's a first term, a second term, a third term, and there may be 79 terms. There may be 37 million terms. There may be an infinite number of terms, but that's what a sequence is. So again, like I said in the last video, sequences and series will have, frankly, not much to do with anything else we've studied in this course. And the real deeper reasons to study this, I hope you continue on in your studies of mathematics. Hopefully, eventually, you'll wind up in second semester calculus, where it really, really all comes together, and you can see how a lot of things are done in the world that really go on behind the scenes and most people don't ever see. So I just say that because I know that more than likely when I first studied this, I thought, why are we doing this? I don't get the point. Why would anybody be interested? But I can assure you there are fantastic reasons to be interested. Well, I mean, we live in the world of the internet. There are many questions that I used to give my students, and I don't anymore because, Google, tap, 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 and you get the answer. So, I'm still tempted to throw out questions, and I will right now. I'm going to throw out a question, and it's a famous question, so you may have heard of it before. So if you have, kind of no fair, and no fair looking this up, but I'm going to ask you a question and just see if you can figure it out. In the next video, we'll talk about it. Like I said, this is not anything I created. It's certainly nothing I invented. But what I would like you to think about is, what is 1 plus 2 plus 3 plus, and keep on adding this up to 100. Actually, let's make, well, try this first. Here, I'll give you a hint. Try it up to 10. I might as well write this the way that we're going to be writing this. I'm going to use a capital or S for sum. Sum, we're adding things up. And the little subscript of 10 means, I guess, we're adding up to the 10th term. First term, second term, all the way up to the 10th term. And here's S sub 100. And then S sub 1000. 1 plus 2 plus all the way up to 1000. And then, well, I mean, here, how about a billion or a trillion? Make it a trillion, huh? So 1 plus 2 plus all the way up to a trillion. This you could probably do in your head, and if not, you could certainly do it on a calculator. This you could certainly do on a calculator. This you could, but think about it. Wouldn't be fun. 1 plus 2 plus 3 plus 4 plus 5 up to 1,000. But you could. This, what's an interesting math question? How long would it take you to do this if you added up 1 plus 2 plus 3 plus 4 plus 5 plus a million plus a million one plus a million and two? And you're not even close to being there, right? Because a trillion is a million million. So once you got up to a million, you'd have to repeat that process a million times. So you might wonder, could you even do this in a lifetime? I'm not sure I've ever done a calculation. My hunch is no, you couldn't, but I'd really have to sit down and think about it. But I'd be willing to bet $1 that you couldn't do this in a lifetime, even if for some bizarre reason you were I don't know what your only goal in life was to do this on a calculator. So the idea, or what I'm hinting at, is there's some other way to do this. There's some easier way to do this. There's a way to go about figuring out what these are without having to go through the painful process of adding those up. So think about this again. I mean, if you Google 1 plus 2 plus 3 plus 4, but I bet it'll come up how to do it. So that's not what I meant. See if you can think about it. And then I'll tell you the story about Gauss when he was in kindergarten and was confronted with this. So until the next video, start reading chapter 12. There's some new terminology, like I said, sequences, series, and there are some new symbols that we want to cover. And so I'll start incorporating those little by little in the videos. Please, please, please start reading and studying chapter 12.